Hello, welcome to this short video on version 6, phase 6 if you like. It's only a couple of changes in phase 6. I've split the project again, so it's now got an extra. I've split the assemble and disassemble function really into two files. fsm.c now has a load and save for memory, so you can actually save great big chunks of memory, sort of the whole lot of it or little bits of it to and from a file. This just means that when you've created a program, you can save it out and then load it back, and it's kind of relocatable, because if you decide to save a memory location to a file, then you can load it back either from that file into the same memory location or into a different one. And I've added an assembler, a line assembler. It's not a complicated assembler, it's not a 2-pass assembler or anything. It just takes an input from a line, converts the mnemonics into hexadecimal opcode, and stuffs it into memory. But it makes inserting stuff into memory a little bit more programmatical. Okay, so as usual, within the program we've got a help function. This help function now has got the comma and full stop, which are sort of legacy things that I remember using years ago on a 6502 monitor on a Commodore 64. The assembler is just the A command, so we'll go through that in a little while. But at the moment, what I'd like to sort of demonstrate is if we take a look at, say, memory sort of A0 through AAAF, which we've seen before, it's all zeros. Now what we can do is we can save that memory out using whichever command it was to save it out, which was the full stop. So we can save out AAA0 through AAAF to Mem Dump, and it's done it. And if we now fill AAA0 to AAAF with all Fs, and we can have a look at that, AAA0 through to AAAF, so it's now all Fs. If we reload the file, what the file it was Mem Dump, wasn't it? Mem Dump, there we go. And then we go and have a look at that again with AAA0 to AAAF. It's put the all zeros back in, which we saved out originally. So there's a file on disk now called Mem Dump, which has got the characters. Basically, it's just a very simple file. The start of the file it creates, it puts the start and the end address. And at the end of and the rest of the file is just the memory bytes, and there's a disk function here. So the function's fairly long in comparison. What it does is it takes input from the user from the CLI as the other ones do, and it says if the number of arguments is 2, then the implication is that all we're getting is the command and the file name. So therefore the file name must be on token 1, and the state is 0. So that the state is used to sort of say use the start and end addresses that are saved in the file. But if j equals 3, then the implication is that actually token 2 is where is our file name, but token 1 is our start address. So we go through the same rigmarole as we did before, having a look at whether or not our start address is hexadecimal or decimal. Then we convert it into a proper number from a string, and then we set the end address to 65535. So we basically say, look, we know there's a start address, just keep loading that file up until the point where you hit or go, if you go beyond that, then that's our check limit, and we set the state to 1 to say that actually we are ignoring the start address from the file because we've been given it from the user. And then all it does is it comes down here, and this is the save version of it as well. This is the next bit that says if case is 1, so if we actually want to save rather than load, and the same thing, and there's a few error checking there. So if the conditions aren't met, then there's various error conditions that say, wrong file name or wrong number of inputs and things. And then this basically opens the files as a fancy way of opening the file, because all it does is it says there's the file name that we took from the command line. This is one of those ternary ifs. It says if the flag is 0, then we're reading, and otherwise we're not, we're writing. So that's just a fancy way of creating a file open without having to write multiple lines of code. And then we go and have a look at the flag and say, well, if it's a load, then we load, and if it's a save, then we save. So on the load here, we say if the state equals 0, so therefore if we're taking the start address from the file rather than the user input, then go and get the first 16 bits from the file, and then go and get the next 16 bits from the file. Otherwise, we ignore the start address, so what we do is we just basically load it in using the end address there, and then we load the real end address. Then we do some checks, and this check here is just to say if are we going to run out of memory. So if you think about it, if the end address that we've got minus the start address, because this is our temporary start address, okay, added, it will give you a result. So AAAF in our case minus AAA0 will give us F. So if start address plus F start address plus F is less than 65536, then we're not going to run out of memory. Therefore, load the file. Otherwise, we are going to run out of memory, and tell them so. And the same thing happens with the save. The save's not quite as complicated, because all we're doing is we just keep running up until the point where the memory's saved. So that's basically the load and save routine. It's not that complicated really. It's just logic wrapped around it. Most of it's error checking. The line assembler is a little bit nice. So what we've got is we can put in the assemble command, and let's say we say AAA0 just to be awkward, and it throws us into the line assembler. And the line assembler allows us to do things like load the accumulator with say an immediate value of 4, and it's thrown us onto AAA2, so we know that was a good command. Then we can we can do checks if we wanted to. So we could do branch if not equal to 0, and we could branch to seed come here to the X address of seed, like that. Bad opcode, you see. It's given us a bad opcode on you see, now that's interesting. So what that actually is telling us, although it says bad opcode, it's not. That's me being silly, because what we've done there is we can only go backwards and forwards, can't we? A few bits with the branch. So if we go we could do this, for example, and that would take that. But notice several things. First of all, it told us there was an error, and it threw us back to the memory address where we were going, where we should have been. And secondly, it did an integrity check. Now, although it says bad opcode, what it really means there is you it's bad operand really, because we put in an operand that was far too big, because the branch instruction is only a 2 byte instruction. And we've got store commands, so we could store the accumulator, and we could store it. We could do something clever here, because we could use an indirect store. So, for example, we could we could say something like AA, X. Alright, we use the index there, and it'll take that, no problem at all. And the carriage return on its own will stop us from will exit the assembler. So if we now do a disassemble for AAA0 through to AAA4, you can see the commands we put in, and you can see that it has actually interpreted it properly, and that that program will run as you would expect it. Now, in this video, I don't intend to sort of go into the assembler in too much detail. I will put another video together on the assembler, specifically on the assembler, because I find it quite an interesting topic, and I found it quite an interesting thing to learn to do. It's been a very, very long time since I last did anything like this, sort of 30 years or something. So as an exercise now, I found it quite useful. So there we go. So that's the end of this particular video. If you've got any comments, then please leave them, and please subscribe.